The nearest star to our Sun has a planet, not a gas giant, not a frozen rock at the edge of a distant system, a world roughly the size of Earth, orbiting within the zone where liquid water could exist, sitting in the darkness just 4 light years away. In the scale of the galaxy that is almost close enough to touch, the planet is called Proxima Centauri b, and on paper, it is one of the most promising candidates for life ever found beyond our solar system. Then you look at the star it orbits. Proxima Centauri is violent in a way that most stars are not. It erupts, it floods the space around it with radiation storms and bursts of energy powerful enough to briefly make it thousands of times brighter at certain wavelengths. Any planet sitting close enough to receive warmth from this star is also close enough to absorb everything that comes with it. By every instinct, this should end the conversation. A star this hostile, this restless, orbited by a world this exposed, it should not be a place worth looking at twice. And yet scientists keep returning to it, because the more carefully they model what might be happening on that planet, the atmosphere, the surface, the conditions, the less certain the conclusion becomes that nothing could survive there. The question is no longer simply whether Proxima b could support life. It is what 4 billion years of evolution might produce on a world where the sky has always been trying to kill everything underneath it, and whether, if something did survive there, we would even recognize it as life at all. Tonight, we go there. Before we do, quick favor. If you find yourself coming back to videos like these, hit subscribe so you don't miss the next one. It makes a bigger difference than you might think. Let's talk about what we actually know. Long before anyone knew a planet circled this nearby star, astronomers were trying to understand a faint point of light hidden among brighter neighbors. In 1915, a Scottish astronomer named Robert Innes, working at the Union Observatory in Johannesburg, identified Proxima Centauri as the closest known star to our Sun. Across more than a century of observation, that discovery has remained unchanged. The star itself belongs to a category known as a red dwarf. A red dwarf is a star much smaller, cooler, and dimmer than our Sun. It burns its hydrogen fuel at an extraordinarily slow rate. While stars like our Sun live for billions of years, red dwarfs can endure for trillions of years, remaining active long after larger stars have exhausted their fuel. From Earth, Proxima Centauri sits about 4.24 light years away. That distance is immense by human standards, yet within the scale of the Milky Way galaxy, it is remarkably close. It is our nearest stellar neighbor. The planet orbiting it, Proxima Centauri b, was announced in 2016 after years of careful measurements. Astronomers did not see the planet directly. Instead, they detected its influence on the star. This technique is called the radial velocity method. As a planet circles a star, its gravity causes the star to move slightly as well. That motion creates tiny shifts in the star's light spectrum, allowing researchers to infer the presence of an unseen world. What emerged from those measurements was intriguing. Proxima Centauri b has a minimum mass of about 1.17 times that of Earth. It completes an orbit in roughly 11.2 Earth days. The planet circles its star at a distance of approximately 7.5 million kilometers, which is about 4.7 million miles. For comparison, Earth orbits our Sun at roughly 150 million kilometers, which is about 93 million miles. That proximity changes everything. Because the planet travels so close to its star, gravitational forces have almost certainly synchronized its rotation and orbit. This process is called tidal locking. One hemisphere continually faces the star, the opposite hemisphere continually faces away. Much like Earth's moon always presents the same face toward us, Proxima Centauri b likely shows one side to its star forever. Yet, despite this unusual arrangement, the planet occupies what astronomers call the habitable zone. This is the region around a star where temperatures may allow liquid water to exist on a planetary surface under suitable conditions. It is neither obviously frozen nor obviously scorched, but three essential pieces remain unknown. We do not know whether Proxima Centauri b possesses an atmosphere. We do not know whether it generates a magnetic field. We do not know whether liquid water exists there today. Those uncertainties are not barriers. They are among the most active scientific questions in modern exoplanet research, and each one opens a path into territory far stranger than we once imagined. Imagine tracing a path across a world where geography never changes its relationship with the sky. Every mountain, every plain, every shoreline remains locked beneath the same conditions for ages beyond comprehension. On Proxima Centauri b, rotation and orbit appear to have fallen into perfect synchrony, creating a planet divided into two enduring realms. One hemisphere faces the star continuously, the other never does. On the illuminated side, radiation pours down without interruption. There is no sunset to provide relief, and no seasonal shift to redistribute energy. If the planet lacks a substantial atmosphere, surface temperatures could climb high enough to vaporize certain minerals. Rocks exposed for millions of years would endure the same relentless stellar direction. Above them, the red star would remain fixed in place, never crossing the sky, never marking the passage of a day. The far side presents a different reality. There, darkness stretches without end. Energy arriving from the star becomes almost non existent. Temperatures could fall to 100 degrees below 0 degrees Celsius, or 148 degrees below 0 degrees Fahrenheit, and perhaps lower in some regions. Under such conditions, atmospheric gases might condense directly onto the surface, collecting as frost or ice. Entire landscapes could become repositories for material that elsewhere remains airborne. Yet the most intriguing territory may lie between these extremes. Separating the two hemispheres is the terminator zone, a broad transitional region where perpetual twilight prevails. This is not a narrow boundary drawn across the ground. Depending on atmospheric conditions, it could extend for thousands of kilometers, which is about hundreds to thousands of miles, wrapping completely around the planet like an unbroken ring. Research conducted by scientists at the University of California, Irvine, and published during 2023 explored this possibility in detail. Their climate models suggested that under several plausible atmospheric scenarios, temperatures along parts of this ring could remain between 0 degrees Celsius, or 32 degrees Fahrenheit, and 30 degrees Celsius, or 86 degrees Fahrenheit. Conditions within that range allow liquid water to persist. From this twilight belt, the star would occupy a permanent position at the horizon. It would never rise, it would never set. One half of the sky would remain dominated by its reddish glow, while the opposite direction would lead gradually into darkness. Such a configuration reshapes the atmosphere itself. Warm air would continually rise over the day side and move toward the colder hemisphere at higher altitudes. Cooler air would return across the surface. The result is a global circulation pattern operating without seasonal interruption, sustained across billions of years. But this planetary airflow does more than move heat. It distributes energy, transports moisture, and regulates temperature differences across the world. In many ways, it functions like a circulatory system for the entire planet. Every organism that might exist on Proxima Centauri b depends on the behavior of this narrow ring, and anything living there has had billions of years to become exquisitely adapted to those exact conditions. Some stars spend their lives in relative stability, releasing energy through rhythms that remain predictable across vast spans of time. Proxima Centauri belongs to a different category entirely. It is a flare star, a star prone to sudden eruptions that unleash tremendous bursts of radiation into the surrounding space. These outbursts are not rare curiosities. They are part of the star's nature. When astronomers observed Proxima Centauri during 2016, they recorded a flare more powerful than any solar flare ever measured from our own Sunday. The event highlighted a growing concern among planetary scientists. A world orbiting so close to this star would receive far more than warmth. It would also endure every violent pulse the star produced. The concern deepened several years later. On the first day of May in 2019, an extraordinary superflare was observed simultaneously by 9 different telescopes. At peak intensity, the eruption lasted only a few seconds. Yet during that brief interval, Proxima Centauri became roughly 14,000 times brighter in ultraviolet wavelengths than normal. For any nearby planet, that matters enormously. Ultraviolet radiation carries enough energy to alter molecules directly. A study published during 2017 estimated that a major flare could expose the surface of Proxima Centauri b to approximately 65,000 times the ultraviolet flux received at Earth's surface during the calmest solar conditions. The consequences extend down to biology's most fundamental machinery. Within living cells, deoxyribonucleic acid stores hereditary information. Ultraviolet radiation can break chemical bonds inside those molecules. Under extreme exposure, damage accumulates rapidly. Researchers describe one particularly destructive mechanism as photolysis-resistant dimerization, a process in which molecular structures become altered in ways that ordinary repair systems struggle to reverse. On Earth, life benefits from a powerful layer of protection. High in the atmosphere, ozone absorbs between roughly 97 and 99% of incoming ultraviolet radiation. Most living things have evolved beneath that shield for hundreds of millions of years. Remove it, and Earth's surface becomes a far harsher environment. But no confirmed ozone layer has been detected around Proxima Centauri b. Whether such a layer exists depends upon atmospheric chemistry. Its long-term survival may also depend upon additional planetary defenses. The details remain uncertain. Yet one fact changes the entire perspective. These flares did not begin recently. Proxima Centauri is approximately 4,850,000,000 years old. For nearly that entire span, the star has been producing energetic eruptions. Any organism that emerged on its nearby planet would have encountered this radiation from the very beginning of its evolutionary history. Viewed that way, the challenge becomes stranger. We are no longer asking whether life could endure an occasional catastrophe. We are considering what biology becomes after billions of years immersed in a world where radiation is woven into the background conditions of existence itself. Before any ecosystem can flourish beneath such a star, however, the planet needs protection. The first possible shield is a magnetic field. Deep beneath our feet, far below oceans and continents, Earth's protection begins in a place no human has ever visited. Within the planet's liquid iron outer core, enormous currents of moving metal generate a magnetic field that extends far into space. As Earth rotates once every 24 hours, heat escaping from the interior helps drive this constant motion. That invisible shield matters enormously. Charged particles streaming from the sun encounter the magnetic field long before they reach the surface. Many are diverted away, forced into new paths around the planet. Without that protection, Earth's atmosphere and surface environment would be exposed to a far harsher space weather regime. When scientists first considered Proxima Centauri b, this comparison created a problem. The planet almost certainly completes one rotation in the same time it takes to complete one orbit, roughly 11.2 Earth days. For years, standard models suggested such slow rotation would weaken the internal processes needed to sustain a powerful magnetic dynamo, a dynamo being the mechanism that generates a planetary magnetic field through the movement of electrically conducting material. The conclusion seemed straightforward. A weak field implied limited protection. Limited protection implied severe atmospheric erosion. Severe atmospheric erosion reduced the prospects for long-term habitability. Across much of the astrobiological community, this became one of the most frequently cited reasons for skepticism. But planetary science rarely stays settled for long. During 2025, researchers revisited the problem using updated interior models. Instead of focusing primarily on rotation speed, they examined the consequences of the planet's larger mass. A more massive world experiences greater gravitational compression within its interior. That compression generates additional heat. Radioactive elements trapped inside the planet contribute further energy as they slowly decay. The revised calculations produced a different picture. If sufficient heat remains trapped within the interior, vigorous convection may continue inside a liquid metallic core, even when rotation is slower than previously assumed. Convection is the process by which hotter material rises while cooler material sinks, creating continuous circulation, and where sustained circulation exists, a magnetic dynamo may follow. Suddenly, the debate reopened. The earlier consensus no longer appeared secure. Some models now suggested that Proxima Centauri b could maintain a magnetic field substantial enough to alter the entire habitability discussion. Even a field possessing roughly half the strength of Earth's could deflect much of the incoming stellar wind and significantly reduce the environmental consequences of the star's activity. Yet, there remains a frustrating limitation. No operational telescope can directly measure an exoplanetary magnetic field today. The required techniques remain under development, forming an important goal for future observatories. For now, astronomers must search indirectly. The James Webb Space Telescope cannot detect the field itself. What it can examine are clues. An atmosphere that survives across billions of years suggests protection. An atmosphere that has vanished suggests vulnerability, which is why these questions refuse to separate. The magnetic field and the atmosphere are intertwined, each revealing part of the same story while constraining the possible answers to the other. Among all the uncertainties surrounding Proxima Centauri b, one stands above the rest. Strip away every other question for a moment, and we arrive at a single issue that determines almost everything else. Does the planet still possess an atmosphere? The distinction is profound. A rocky surface without air is exposed directly to space. Temperatures swing more dramatically. Radiation reaches the ground with fewer obstacles. Water struggles to remain stable. Chemistry proceeds along different paths. With an atmosphere, an entirely different planetary story becomes possible. The challenge begins with the star. Proxima Centauri continuously releases a stellar wind, a stream of electrically charged particles flowing outward through space. Estimates suggest this wind may be roughly 2,000 times stronger than the solar wind produced by our Sunday. Across immense spans of time, such particle streams can gradually erode a planet's atmosphere, carrying away gases molecule by molecule. We have already seen a version of this process closer to home. Mars once possessed a thicker atmosphere than it has today. Over approximately 3,500,000,000 years, interactions with the solar wind stripped away much of that protective envelope. Yet Mars circles a far less aggressive star than Proxima Centauri. If atmospheric loss occurred there, the concern becomes difficult to ignore here. But another world offers a different lesson. Venus lacks a global magnetic field and exists closer to the Sun than Earth. Despite that vulnerability, it retains an atmosphere approximately 90 times denser than our own. The reason lies beneath its surface. Volcanic activity releases enormous quantities of gas from the interior, continuously replenishing atmospheric material over geological time. That possibility changes the conversation. If Proxima Centauri b remains geologically active, its atmosphere may not be a relic struggling to survive. It may be a system under constant renewal. The planet's larger mass could help preserve internal heat. Gravitational forces may contribute additional heating within the interior. Together, these processes could sustain volcanism for billions of years. Fresh gases would continue rising upward. The atmosphere would continue rebuilding itself. Evidence supporting this scenario emerged during 2024 when researchers at the University of Arizona modeled atmospheric chemistry under several plausible conditions. Their results suggested that an ozone layer could form and remain stable if volcanic outgassing supplied gases at moderate rates. Ozone, of course, plays a crucial role in filtering harmful ultraviolet radiation. Yet models can only carry us so far. Real answers require observation. That is where the extremely large telescope enters the story. Rising in Chile's Atacama Desert, this observatory is being built specifically to analyze nearby exoplanet atmospheres with a level of precision beyond any telescope operating today. Among its most important targets sits Proxima Centauri b. For the first time, astronomers may soon measure the composition of air around this world rather than merely speculate about it. And from this point onward, we will proceed with a working assumption. An atmosphere exists. Once you grant the planet air, the question shifts from whether life could persist there to what form that life might take. Every ecosystem begins with an energy source. Before bodies, before behavior, before evolution can explore countless possibilities, something must capture energy and convert it into living chemistry. On Earth, that role is largely played by sunlight. Yet the light reaching Proxima Centauri b is fundamentally different from the light that shaped our world. Most of the star's energy arrives as near-infrared radiation. Human eyes cannot see it. Even the visible portion of Proxima Centauri's output differs dramatically from our familiar experience. The star emits a dim, deep red glow. If you could stand within the habitable twilight regions we have been considering, the star would appear roughly 500 times dimmer than the Sun appears from Earth in the wavelengths that human vision can detect. Life would adapt accordingly. On Earth, photosynthesis evolved beneath a yellow-white star. Plants and algae developed pigments tuned to absorb the wavelengths most commonly available. Chlorophyll, the pigment responsible for the green appearance of most vegetation, captures energy primarily from red and blue visible light. A world illuminated mainly by near-infrared radiation presents a different challenge. Any organism relying on photosynthesis would need pigments capable of harvesting longer wavelengths, carrying less energy per photon. Evolution would not begin from Earth's solutions. It would respond to a different energy landscape. Scientists have already explored this possibility using life that exists on Earth today. During 2024, Researchers working through biosignature simulations at the Goddard Institute for Space Studies used a bacterium called Blastochlorus viridis as a biological template. This microorganism performs photosynthesis using near infrared light and reflects a distinctive purple coloration. The simulations were grounded in laboratory measurements. Researchers examined actual absorption and reflection properties rather than relying entirely on theoretical assumptions. The resulting model organisms were designated Blastochlorus viridis like organisms, representing hypothetical photosynthetic life adapted to conditions around Proxima Centauri. Their appearance would be striking. Instead of broad green landscapes, a biologically active surface could display dark purple tones approaching black. Vast living regions might absorb nearly every useful wavelength reaching the ground, reflecting only a narrow range of light back into space. That reflection pattern matters. From across interstellar distances, astronomers cannot inspect individual organisms. They search for signatures. A signature is a measurable feature indicating a particular process may be occurring. Earth's vegetation produces a recognizable spectral feature called the green vegetation red edge. The modeled Proxima organisms generate an equivalent marker known as the near-infrared edge. This signature occupies a specific region of the spectrum. It can be predicted. It can be modeled. Future direct imaging observatories are being designed with the precision required to search for exactly this kind of signal. For the first time, we possess more than speculation. We know which wavelengths to examine. We know the appearance such life could create across an entire world. And if living surfaces are shaping the planet beneath that reddish sky, they may already be producing clues detectable from light years away. The next question becomes more intimate. If organisms evolved beneath this unfamiliar illumination, how would they perceive the world around them? Consider how much of your understanding of reality depends upon the particular biology of your eyes. Every color you recognize, every landscape you imagine, every familiar distinction between brightness and darkness emerges from a sensory system shaped by a specific star. Human vision evolved beneath the spectrum produced by our sun, and our eyes became most sensitive to the wavelengths most abundantly available. That outcome was no accident. The peak sensitivity of human vision falls near green light, close to the region where our star emits much of its visible energy. Across hundreds of millions of years, animal eyes and solar output became linked through evolution. A different star changes that relationship. On Proxima Centauri b, any visual system would likely evolve around deep red and near infrared wavelengths. Organisms would tune their sensory organs toward the radiation most consistently available in their environment. To such creatures, portions of the electromagnetic spectrum that appear completely dark to us could form the foundation of ordinary perception. This possibility carries unusual consequences. Near-infrared radiation interacts with biological tissue differently than visible light. Many tissues become partially transparent at these wavelengths. On Earth, some animals possess limited infrared sensitivity, allowing them to detect heat patterns or subtle physiological signals. Expand that capability dramatically, and perception begins to take unfamiliar forms. A fully near-infrared adapted organism might detect structures hidden beneath surfaces. Thin layers of rock could reveal internal features. Living bodies might appear as layered arrangements of vessels, organs, and circulating fluids rather than opaque shapes. The distinction between exterior and interior could become less absolute than it is for us. Vision itself might also change physically. The twilight conditions across much of the habitable zone would reward efficient light gathering. Large eyes collect more photons. Wide pupils emit more radiation. Dense populations of photoreceptor cells increase sensitivity. Similar pressures shaped the enormous eyes of certain deep ocean fish living in environments where very little light penetrates. But evolution rarely commits to a single solution. If near infrared information proved limited or unreliable, other senses could become dominant. Ground vibrations might carry valuable environmental data. Organisms could detect subtle seismic disturbances through direct contact with the surface. Sensitivity to electromagnetic changes might allow living systems to respond to disturbances associated with stellar activity. Chemical sensing could become extraordinarily refined, tracking gradients in the atmosphere with a precision difficult to imagine on Earth. Time itself may feel different as well. On Earth, biological clocks are strongly influenced by changing light conditions. Circadian rhythms regulate sleep, activity, hormone production, and countless internal processes. On a world where illumination remains essentially constant within a given region, that familiar framework weakens. Life may organize itself around different cycles entirely, perhaps tied to environmental chemistry, resource availability, or internal physiological timing. The result is a biosphere perceiving reality through channels largely unavailable to human experience. We can model the physics, we can estimate the pressures guiding evolution, yet the lived experience remains deeply unfamiliar. And if the senses evolved along such unusual paths, what kind of body ultimately emerged to carry them? Take a familiar animal from Earth and place it in a stronger gravitational field for millions of generations. The transformation would not happen overnight. Bones would thicken gradually, limbs would shorten, weight distribution would shift. Evolution would begin negotiating with physics in a slightly different way. That negotiation may have been underway on Proxima Centauri b for billions of years. Current estimates suggest surface gravity there could be roughly 1.1 to 1.3 times stronger than Earth's. At first glance, that difference sounds modest. You might barely notice it during a single step. Yet evolution does not measure time in moments. It measures time in countless generations. Small forces accumulate. A body repeatedly challenged by greater gravity tends toward stability. Lower centers of mass become advantageous. Broader support structures distribute weight more efficiently. Compact forms require less energy to maintain and reduce mechanical stress on tissues. We see hints of this principle on Earth. Large animals, such as elephants and hippopotamuses, possess stocky proportions because mass and gravity impose constraints that slender bodies struggle to satisfy. Similar pressures operating over immense timescales could shape entire ecosystems on Proxima Centauri b. The result might be a world populated by organisms that appear shorter, wider, and closer to the ground than Earth, creatures of comparable mass. But gravity is only one influence. Radiation remains a constant environmental factor. On Earth, protection against ultraviolet damage exists within every cell. Repair systems continuously correct molecular injuries caused by ordinary sunlight. Most organisms rarely notice this process because it occurs automatically. On Proxima Centauri b, those mechanisms would likely be far more advanced. Consider a bacterium called Deinococcus radiodurans. This microorganism can survive radiation doses approximately 1,000 times greater than those lethal to humans. It accomplishes this through remarkable biological strategies. Multiple copies of its genetic information remain available as backups, while specialized enzymes rapidly repair damaged deoxyribonucleic acid. What appears extraordinary on Earth could become commonplace elsewhere. Multicellular organisms, evolving beneath harsher conditions, may inherit similarly robust repair systems as standard cellular equipment. Such capabilities would not mark exceptional species. They would define ordinary life. Protection could extend outward as well. Dark biological pigments, capable of absorbing harmful radiation, would offer additional advantages. Earth uses melanin for this purpose. On Proxima Centauri b, equivalent compounds may be more abundant, more effective, and integrated into nearly every living surface. Some organisms might go further still. Mineralized armor already appears throughout Earth's biosphere. Shells, bones, and exoskeletons incorporate environmental materials into living structures. Given sufficient evolutionary pressure, organisms could develop dense protective layers containing silicates, calcium compounds, or other minerals available in their surroundings. Body plans would therefore reflect multiple demands simultaneously. Gravity encourages compactness. Radiation encourages shielding. Environmental stability encourages specialization. Together, these forces sculpt life into forms shaped by circumstances unlike those that guided evolution on Earth. Yet all these possibilities share one assumption. They imagine organisms living on the surface. What if the most successful life on Proxima Centauri b found a different path entirely, remaining beneath the ground and beyond the reach of the sky? The story begins far below an ocean's surface, in a place no sunlight has ever reached. In 1977, the research submersible Alvin descended into the darkness of the Galapagos Rift beneath the Pacific Ocean. Scientists expected barren seafloor. Instead, they found abundance. Life was everywhere. Dense communities surrounded towering hydrothermal vents, places where mineral-rich water erupted from Earth's crust after being heated deep underground. These ecosystems existed at depths where sunlight could not penetrate. No green plants grew there. No photosynthesis powered the food chain. Yet thousands of organisms flourished. A long-held assumption collapsed. Before that expedition, biologists generally believed all life on Earth ultimately depended upon solar energy. The discovery at the Galapagos Rift overturned that idea in a single voyage. An entirely different pathway existed. It is called chemosynthesis. Chemosynthesis is the process through which organisms extract energy from chemical reactions rather than light. Certain microbes consume compounds released from geological activity, including hydrogen, sulfide, methane, and iron-rich minerals. Those microbes become the foundation of entire ecosystems. Everything grows upward from them. Around Earth's hydrothermal vents live remarkable creatures found nowhere else. Giant tube worms can exceed 2.4 meters in length, which is about 7.9 feet. Specialized shrimp possess light-sensitive organs across their backs rather than conventional eyes. Unique crustaceans roam the vent fields. Entire communities depend upon chemistry rising from the planet below. The sun contributes nothing. If a catastrophic event extinguished sunlight reaching Earth, these deep ecosystems would continue largely unchanged. Their energy source lies beneath them rather than above them. That possibility becomes especially important when we turn our attention back to Proxima Centauri b. If gravitational forces from its nearby star generate ongoing tidal heating, then the planet's interior may remain geologically active for immense spans of time. We already know a comparable process operates on Jupiter's moon Io, where constant gravitational squeezing drives extraordinary volcanic activity throughout the moon's interior. The mechanism is well understood. Heat generated inside Proxima Centauri b could sustain volcanic systems, circulating groundwater, and extensive hydrothermal networks beneath the surface. Under those conditions, hydrothermal vents become more than plausible. They become expected. But something remarkable follows from that conclusion. Chemosynthetic ecosystems would be largely insulated from many of the dangers discussed earlier. Stellar flares remain above, atmospheric erosion remains above, harmful radiation remains above. The biological engine operates within the geological layer itself, powered by internal heat and chemical gradients. Life would continue. Many astrobiologists regard chemosynthetic environments as one of the strongest candidates for the birthplace of life on Earth. Some researchers even argue that biology powered by chemistry may be more ancient and more widespread than biology powered by sunlight. That idea shifts our perspective. Perhaps photosynthesis is not the default pathway for living worlds. Perhaps it is merely one branch among many. And in the narrow habitable regions of Proxima Centauri b, geological heat rising from below could meet stable surface conditions above, creating a boundary where two different worlds touch the same landscape. Imagine a shoreline where the weather never truly changes. No spring follows winter, no summer gives way to autumn. The same forces act on the same waters, year after year, across spans of time so vast that entire evolutionary histories unfold beneath an unchanging sky. For astrobiologists, liquid water remains the working assumption when discussing life. This is not because we know life cannot exist without it. Rather, every living system ever discovered on Earth depends upon water, and its chemical properties make it exceptionally effective for transporting nutrients, enabling reactions, and stabilizing complex biological structures. Yet on Proxima Centauri b, water would behave according to a very different planetary script. The contrast begins with geography. One hemisphere continuously faces the star, receiving an uninterrupted supply of energy. If oceans exist there, their surfaces may remain persistently warm, encouraging evaporation at a constant rate. Water vapor would rise endlessly into the atmosphere, forming extensive cloud systems that could spread across vast regions. Those clouds matter. Reflective cloud cover can send incoming radiation back into space, reducing surface heating below. In this way, evaporation and cloud formation may become part of a self-regulating climate process, preventing temperatures from climbing as rapidly as simple models might suggest. Far away, conditions reverse. Across the permanently dark hemisphere, ocean surfaces would steadily lose heat. Temperatures could decline enough for extensive ice formation. Over immense periods, a frozen shell might spread across much of the night side, creating a landscape where liquid water retreats beneath layers of ice. But water never remains still for long. A powerful temperature contrast between hemispheres would establish a permanent circulation system. Warm surface water would drift away from illuminated regions toward the boundary zone. At greater depths, colder and denser water would flow back toward warmer areas, completing a continuous planetary loop. This is not seasonal circulation. It is not driven by changing weather patterns or shifting sunlight. Instead, it functions as a long-term thermodynamic engine powered by the same temperature gradient for billions of years. Along the twilight boundary, another process emerges. As surface waters move and mix, colder deep water can rise upward. This phenomenon is called upwelling, a process where nutrient-rich water from below reaches the surface. On Earth, similar upwelling zones support some of the most productive marine ecosystems ever observed. The implications are significant. Regions receiving a constant supply of nutrients and moderate temperatures could become biological strongholds, places where life gains access to both energy and chemical resources. Beneath the frozen hemisphere, another possibility remains. Internal planetary heat, generated deep below the crust, could keep water liquid under thick layers of ice. Europa, one of Jupiter's moons, offers a familiar comparison. Its buried ocean remains one of the most compelling environments for potential life within our own solar system. Taken together, Proxima Centauri b may host several water worlds at once: open ocean near the twilight regions, vast night-side ice fields, hidden liquid reservoirs beneath frozen surfaces. Each environment would possess distinct chemistry, distinct energy flows, and potentially distinct living systems. Water alone, however, never completes the story. Life also requires a continuous supply of useful chemical ingredients, and those ingredients ultimately come from the planet itself. Far beneath any ocean, ice sheet, or habitable shoreline, forces beyond direct observation continue their work. Long before biology can shape a world, the planet itself must remain active. Its interior must move, fracture, circulate, and release energy outward. Proxima Centauri b may possess exactly that kind of restless interior. Its greater mass creates stronger gravitational compression throughout the planet. Every layer presses more intensely upon the layers beneath it. That pressure generates additional internal heat, giving the world a larger thermal reservoir than a planet with precisely Earth's mass. The effect is continuous. Rock deep below the surface retains energy for immense spans of time. Heat rises slowly through the mantle, the thick layer of hot material between the crust and the core. Yet gravitational compression may be only part of the story. Another source operates constantly. The planet circles extremely close to its parent star. As gravity pulls on Proxima Centauri b, the interior experiences repeated deformation. The crust and mantle flex slightly during orbital motion. Those tiny distortions generate friction. Friction becomes heat. This process is called tidal heating. The mechanism already exists elsewhere in dramatic form. Jupiter's moon Io provides the most striking example known. Constant gravitational interactions squeeze and stretch that moon so effectively that it hosts more than 400 active volcanoes. No other body in our solar system displays comparable geological intensity. Io is powered from within. If Proxima Centauri b experiences even a modest fraction of that tidal heating, volcanism becomes highly likely. Volcanoes release gases trapped below the surface. This process, known as outgassing, transfers material from the interior into the atmosphere. That connection matters enormously. A world constantly replenishing atmospheric gases can replace material gradually removed by stellar activity. The atmosphere becomes part of an ongoing cycle rather than a finite resource slowly disappearing into space. But geology contributes more than air. Volcanic regions on Earth host some of the most chemically diverse microbial communities ever discovered. Acidic hot springs support organisms thriving in conditions once thought impossible. Superheated geyser systems sustain entire ecosystems. Black smoker vents along the ocean floor provide energy-rich environments where ancient biological lineages continue to survive. Many researchers regard such locations as windows into Earth's earliest biological history. Geological activity also drives nutrient circulation. Minerals buried deep underground eventually reach surface environments through eruptions, hydrothermal systems, and chemical weathering. Once released, those elements dissolve into water, enter ecosystems, and become biological building blocks. Life gains raw materials. Earth possesses another powerful geological process. Carbon dioxide moves between atmosphere, ocean, and rock through a long-term cycle operating across millions of years. Volcanism returns carbon dioxide to the atmosphere after chemical and biological processes lock it away within minerals and sediments. A geologically active Proxima Centauri b could sustain a comparable stabilizing system. Such feedback mechanisms help moderate planetary conditions despite external variability. Seen from this perspective, geology is not merely scenery beneath life. It may be the central engine driving everything above it. On Proxima Centauri b, the boundary between the living world and the planet itself could be extraordinarily thin, with surface biology remaining intimately connected to processes unfolding deep below the crust. Time changes the scale of every question we have asked so far. A planet may possess water, geology, an atmosphere, and sources of energy, yet none of those factors alone determine what life becomes. Evolution requires something equally important. It requires duration. Our own sun is a middle-aged star, formed roughly 4.6 billion years ago. It has already consumed a substantial fraction of its hydrogen fuel. Astronomers estimate that in about 5 billion more years, the sun will exhaust the supply, sustaining its current stability. The long chapter that allowed life to emerge on Earth will eventually close. Every star has limits. Proxima Centauri follows a very different path. Because it contains far less mass, it burns hydrogen at a dramatically slower rate. Energy leaves the star gradually. Fuel consumption remains extraordinarily efficient. Current models indicate that Proxima Centauri may continue fusing hydrogen for approximately 4 trillion years. The number is difficult to grasp. The universe itself is about 13.8 billion years old. Against a lifespan measured in trillions of years, Proxima Centauri has barely begun its existence. It has consumed less than 1/10 of 1% of its available hydrogen fuel. The star is still young. Meanwhile, Proxima Centauri b appears to be approximately 4.85 billion years old, remarkably similar to Earth in age. If life emerged there early in planetary history, then biological evolution has already been operating for roughly the same duration as it has on our world. But Earth provides an important lesson. For nearly the first billion years, life remained microbial. Single-celled organisms dominated every environment. Biological innovation certainly occurred, yet structural complexity remained limited. Cells refined chemistry long before they built bodies. The transition took immense time. Complex multicellular organisms appeared only around 600 million years ago, almost 4 billion years after the first known life emerged. Evolution advanced steadily, yet the journey from microbes to large organisms occupied most of Earth's biological history. Suppose that pattern is even approximately universal. If similar timescales apply elsewhere, then Proxima Centauri b may already be experiencing its age of complex life. The planet has had sufficient time for ecosystems to diversify, adapt, compete, and transform across geological eras, extending far beyond human comprehension. And unlike Earth, the clock is hardly ticking. No future expansion into a red giant threatens the planet within the next few billion years. No approaching stellar death imposes a near horizon on biological development. The evolutionary runway stretches outward, almost beyond imagination. Generation after generation could continue. Species may rise and disappear, Entire ecosystems may transform repeatedly. New forms may emerge from old ones across intervals longer than the current age of the universe itself. Viewed from that perspective, the question changes fundamentally. We are no longer asking whether life could survive around Proxima Centauri. We are asking what billions of years of persistence beneath a remarkably long-lived star might already have produced. Only 4 light years away may stand a world still near the beginning of its future, with more evolutionary time ahead than our universe has yet experienced. Imagine an organism born into a world that never changes. Across its entire lifetime, the temperature remains familiar, the light never shifts, winds arrive from the same direction, water follows the same routes. The landscape ages through geology, yet daily conditions remain astonishingly constant. That is a profoundly different evolutionary stage. On Earth, life developed beneath endless environmental fluctuations. Seasons alter food supplies. Rainfall patterns expand and contract habitats. Temperature swings reward flexibility. Organisms survive because they can tolerate variation, often carrying biological systems designed for multiple conditions rather than one. Adaptability becomes insurance. Many plants and animals maintain dormant abilities used only during certain times of year. Genes switch on and off as temperatures rise or fall. Migration, hibernation, breeding cycles, and metabolic changes all emerged because Earth repeatedly demands different responses from the same organism. But a tidally locked world changes those incentives. Within a stable terminator environment, the same conditions persist generation after generation. Natural selection no longer rewards maintaining biological tools that may never be needed. Energy spent supporting unused capabilities becomes wasteful. Efficiency gains importance. Over immense spans of time, evolution could remove every unnecessary feature. Organisms would become increasingly tuned to a narrow environmental window. Body structure, metabolism, sensory systems, and reproductive strategies might all converge toward extraordinary precision. Every trait earns its place. Earth's history also includes repeated disruptions, asteroid impacts, massive volcanic episodes, abrupt climate shifts, continental rearrangements. These events destroyed ecosystems, yet they also created opportunities. After extinction removed dominant organisms, surviving lineages expanded into newly available ecological roles. Innovation often followed catastrophe, but a planet sustained by long-term atmospheric stability and persistent internal heat may experience fewer global resets. Evolution would continue, though perhaps without the recurring interruptions that repeatedly reshaped Earth's biological story. A different pattern emerges. Lineages could persist for astonishing lengths of time. Consider the horseshoe crab on Earth, an organism whose overall body plan changed very little across roughly 450 million years. Now imagine similar persistence occurring across entire ecological communities rather than isolated examples. The result might resemble evolutionary stillness. Yet, stability does not automatically mean stagnation. Natural selection never truly stops. Even in an environment that appears unchanged, competition continues. Predators refine hunting methods. Prey improve defenses. Microorganisms adapt to neighboring microorganisms. Small advantages accumulate over vast intervals. Billions of years matter. A stable environment may permit specialization so extreme that Earth provides no useful comparison. Structures could become optimized to remarkable degrees, because they never need compromise. Biological systems often sacrifice peak performance for flexibility. On Proxima Centauri b, flexibility may carry far less value. Perfection becomes attainable. What would happen if evolution spent billions of years refining organisms for one exact climate, one exact light level, and one continuous flow of energy from a star fixed forever in the same place? That possibility leads naturally toward the chemistry beneath the biology itself. If specialization reaches that depth, and if near infrared radiation remains the dominant energy source throughout evolutionary history, entirely new biochemical solutions may have emerged from that long and unbroken experiment at the smallest scale imaginable, beneath every organism, every ecosystem, and every evolutionary story. Chemistry makes the final decisions. Life on Earth appears endlessly diverse, yet it runs on a remarkably uniform foundation. Every known organism stores information using deoxyribonucleic acid. Information is translated through ribonucleic acid. Proteins perform most biological work. Water serves as the primary solvent. Energy moves through cells using adenosine triphosphate. Across bacteria, fungi, plants, and animals, the same biochemical framework persists. That consistency can create a misleading impression. Many astrobiologists view Earth's chemistry as one successful solution rather than the only possible solution. Early Earth provided a particular combination of temperature, pressure, radiation, and available molecules. Evolution worked within those constraints and refined what happened to function. Proxima Centauri b begins with many of the same ingredients. Carbon remains available, hydrogen remains available, oxygen, nitrogen, sulfur, and phosphorus can all participate in complex chemistry. The periodic table does not change between worlds, but the energy feeding those reactions changes substantially. That difference matters. Most incoming energy arrives as near infrared radiation. These photons carry less energy than the visible wavelengths that power the majority of photosynthesis on Earth. Capturing useful biological energy, therefore, becomes a more demanding chemical challenge. Earth already offers a clue. The bacterium Blastochlorus viridis performs photosynthesis using wavelengths far longer than those favored by ordinary plants. Chlorophyll used by many terrestrial organisms absorbs strongly around 680 and 700 nanometers. Blastochlorus viridis operates near 1017 nanometers, extending biological energy capture deep into the near-infrared region. Nature has explored this pathway before. If life emerged around Proxima Centauri b, evolutionary pressure would strongly favor pigments optimized for those longer wavelengths. The molecular structures involved may resemble Earth examples in broad function while differing dramatically in detail. Small modifications accumulated across billions of years could produce pigments capable of harvesting energy with extraordinary efficiency. But energy capture is only part of the challenge. Radiation remains a constant environmental reality. Every living cell would require mechanisms for detecting and repairing molecular damage. On Earth, Deinococcus radiodurans survives radiation levels roughly 1,000 times greater than doses typically fatal to humans. It accomplishes this partly by maintaining multiple copies of genetic information and rebuilding damaged sequences with remarkable speed. Comparable strategies may become standard biology elsewhere. Cells could carry extensive genetic redundancy. Repair enzymes, biological catalysts that accelerate chemical reactions, might operate far faster than any known terrestrial equivalent. Molecular damage that would cripple Earth organisms could become routine maintenance. Another possibility emerges from the planet's geology. Photosynthesis and chemosynthesis need not remain separate pathways. Organisms may combine both approaches, harvesting near infrared radiation when available, while also extracting energy from chemical compounds released through volcanic and hydrothermal activity. Such flexibility would provide resilience across changing local conditions. Viewed from orbit, those countless biochemical decisions accumulate into something larger. Individual molecules shape individual organisms, organisms shape ecosystems, and ecosystems shape the appearance of an entire living world. Long before we land on another world, we learn to read it from afar. Every living planet alters its surroundings. Organisms consume chemicals, release waste products, reshape landscapes, and modify atmospheres. Given enough time, life leaves fingerprints large enough to be seen across interstellar distances. Earth provides the template. Viewed from space, our planet broadcasts several clues. Atmospheric oxygen exists in quantities difficult to explain without biology. Methane is continually replenished by living systems. Vegetation modifies reflected light in a distinctive way, producing a sharp increase in reflectance near 700 nanometers. Researchers call this feature the green vegetation red edge. It is a planetary signature. These markers form the foundation of remote biosignature detection, the scientific effort to identify life without direct contact. Instead of observing organisms themselves, we search for large-scale consequences that biology leaves behind. Proxima Centauri b would be examined through exactly this approach. If photosynthesis operates there using principles broadly similar to those on Earth, atmospheric oxygen could accumulate over geological time. Oxygen is released when organisms split water molecules and harvest the resulting energy. That process may not belong exclusively to terrestrial biology, but oxygen alone proves little. Many gases can emerge from non-biological processes. Interpretation becomes stronger when several atmospheric components appear together. Methane is a classic example. Living organisms produce substantial quantities on Earth, yet volcanoes and geological reactions can generate methane as well. Context matters. Scientists, therefore, search for combinations of gases that become difficult to maintain without continuous biological activity. Each additional measurement narrows the range of possible explanations and strengthens the overall picture. For Proxima Centauri b, the most distinctive clue may come from the surface itself. Earlier modeling studies explored organisms based on Blastochlorus viridis, adapted for harvesting near infrared radiation. Such life forms absorb specific wavelengths and reflect others. The resulting pattern creates what researchers call the near-infrared edge, a measurable jump in reflected light occurring around 1000 to 1100 nanometers. That feature is observable. The proposed Habitable Worlds Observatory was designed with this wavelength range firmly in mind. Its instruments aim to directly image nearby Earth-sized planets and analyze their reflected spectra in extraordinary detail. Preparations have already begun. The National Aeronautics and Space Administration Climate Model, known as Regional Ocean Atmosphere Coupled Ecosystem, three-dimensional, working alongside the Planetary Spectrum Generator, has produced synthetic observations of how Proxima Centauri b might appear if vast regions were covered by these hypothetical organisms. In effect, we already possess rehearsals of the data. From orbit, a biologically active terminator region may not resemble Earth's forests or oceans at all. To human vision, the living surface could appear deep purple, almost black, absorbing much of the dim stellar illumination and reflecting only a narrow range of wavelengths. Against the glow of a red dwarf star, that living band might appear as a dark stain wrapped around the planet's circumference, a biosphere written across an entire world and visible from 4 light years away. Sometimes a scientific mystery begins as a single line on a computer screen. In April of 2019, researchers studying radio observations from the Parkes Radio Telescope in New South Wales noticed something unusual. Buried within enormous volumes of data was a narrowband radio signal arriving from the direction of Proxima Centauri. The signal received a name, BLC 1, short for Breakthrough Listen Candidate 1, immediately drew attention because of its frequency. It appeared near 982.002 MHz, a region not associated with any known natural astrophysical emission mechanism. Stars produce radio waves, so do galaxies and clouds of gas. But narrow-band signals concentrated into extremely thin frequency ranges are generally associated with technology. That distinction mattered. As analysts examined the detection, several details deepened the intrigue. The signal appeared only when the telescope pointed toward Proxima Centauri. When the star shifted across the sky due to Earth's motion, the signal shifted in a matching way. Searches through existing catalogs failed to identify any obvious source of interference. For a moment, the possibility lingered. Yet, science advances through restraint rather than excitement. The observation was not announced publicly. Within the Breakthrough Listen program, a long-running search for extraterrestrial technology, the signal remained an internal candidate awaiting exhaustive scrutiny. Months passed. Researchers compared observations, tested alternative explanations, and searched for repeating patterns. The process moved carefully because extraordinary claims require extraordinary evidence. A signal resembling technology is not evidence of technology. It is only a clue demanding investigation. Then the story escaped the laboratory. In December of 2020, information about the candidate leaked to the Guardian newspaper before the analysis had reached completion. Public interest surged almost immediately. Headlines spread across the world. Many wondered whether humanity had finally intercepted a transmission from another civilization. But the data continued speaking. A peer-reviewed study published during 2021 concluded that BLC-1 was almost certainly radio frequency interference generated by human technology. Researchers examined increasingly subtle possibilities involving satellites, aircraft, and complex interactions between terrestrial transmitters and receiving equipment. The conclusion carried confidence, yet it also carried humility. Investigators could not positively identify the exact source responsible for the signal. They found a probable explanation rather than a perfectly complete one. The remaining uncertainty was documented openly rather than hidden behind stronger claims. That honesty became part of the lesson. You can see how difficult the challenge truly is. A candidate signal may survive many tests and still originate from Earth. Separating an extraterrestrial transmission from humanity's growing cloud of radio noise demands extraordinary precision. But the episode revealed something important. Proxima Centauri is close enough for present-generation radio observatories to detect remarkably subtle signals from its direction. Because of that proximity, it remains one of the highest priority targets in the search for technological life. The listening continues. Breakthrough Listen and other major search programs still return their instruments toward this neighboring star, watching, measuring, comparing, and waiting, while another effort gradually takes shape beside the search itself. We are not only learning how to hear Proxima Centauri, we are beginning to imagine how to reach it. For decades, Proxima b existed as a destination without a road. We could calculate its orbit, estimate its atmosphere, model its oceans, and imagine its biology. Yet between our world and that distant planet stretched more than 4 light years of space, a gulf so vast that conventional spacecraft would require tens of thousands of years to cross it. Then a different idea emerged. In 2016, physicist Stephen Hawking joined entrepreneur Yuri Milner and Mark Zuckerberg to announce Breakthrough Starshot, a research initiative funded initially with $100 million. Its objective was startlingly direct: reach the Proxima Centauri system within a human lifetime. The proposal abandoned many assumptions that had shaped spaceflight since the beginning of the space age. There would be no giant spacecraft, no crew, no massive fuel tanks. Instead, the mission centered on something called a starship, a spacecraft weighing only a few grams. Attached to it would be an ultra-thin sail, engineered from materials measured in layers only atoms thick. The power source would remain on Earth, a vast ground-based laser array producing roughly 100 gigawatts of coherent light would focus its beam onto the sail. Radiation pressure, the tiny push exerted by photons themselves, would steadily transfer momentum to the spacecraft. Light becomes propulsion. Within minutes, calculations suggest the starship could accelerate to roughly 20% of light speed. That is about 60,000 kilometers per second, which is about 37,282 miles per second. At such velocity, distance begins to shrink. The journey to Proxima Centauri would require about 20 years. A child watching the launch could still be young when the spacecraft arrived. But speed introduces compromise. The current baseline design contains no onboard fuel and no braking system. Upon arrival, the probe would race through the system at tremendous velocity, gathering images and measurements during a flyby lasting only hours. Every second would matter. Scientists have spent years examining whether such a mission violates known physics. The answer remains encouraging. Peer-reviewed studies indicate the fundamental concept is physically achievable. But the engineering challenges remain immense, involving materials, science, laser coordination, communications, navigation, and protection against interstellar dust impacts. Even the camera presents difficulties. A spacecraft weighing only grams must still capture meaningful observations while moving faster than any object humanity has ever built. Current estimates suggest imaging resolution near 30 kilometers per pixel, which is about 18.6 miles per pixel. That would be sufficient to reveal large-scale surface structures, coastline patterns, ice distributions, and broad color variations. Then comes the return message. The data would travel home at light speed, requiring approximately 4.24 years to cross the distance back to Earth. Under a plausible development timeline, a probe launched around 2060 could reach Proxima Centauri near 2080, with its observations arriving around 2084. You could be alive to see them. Not simulations, not artist impressions, not computer models. Actual images from another planetary system, carrying details from a world that has occupied human imagination for generations, transforming Proxima b from a place we infer into a place we have finally seen. Sometimes progress arrives as a faint speck beside a star. Long before any probe crosses interstellar space, our understanding of nearby worlds depends on instruments capable of separating impossibly small signals from overwhelming brightness. The James Webb Space Telescope was not originally designed as a specialized atmospheric observatory for nearby rocky planets. Yet, Astronomers continue pushing it toward that role because Proxima b occupies a unique position. It is close enough to tempt every available method. Distance becomes opportunity. During August of 2024, February of 2025, and April of 2025, the James Webb Space Telescope conducted a series of lengthy coronagraphic observations targeting the Alpha Centauri system. This stellar pair is gravitationally associated with Proxima Centauri, making the entire neighborhood an important laboratory for nearby planet detection. The key tool was the coronagraph. A coronagraph blocks starlight before it reaches the detector, creating an artificial eclipse inside the telescope. By suppressing the brilliant glow of the star itself, astronomers gain a chance to see faint nearby objects that would otherwise disappear completely within the glare. The technique demands precision. During the August observation, a team led by Charles Beichman and Anikit Sanghi of the California Institute of Technology identified a bright feature adjacent to Alpha Centauri A. At first glance, it appeared intriguing. The signal possessed characteristics expected from a planetary object orbiting close to the star. Then it vanished. When astronomers examined the February and April observations, the bright feature was no longer visible. Ordinarily, that might suggest an observational artifact. But the team's orbital analysis offered another possibility. A genuine planet moving along a close orbit could easily shift into a position where detection became impossible during later observations. The evidence remained ambiguous. Yet the observation carried importance regardless of the candidate's ultimate identity. It demonstrated that the James Webb Space Telescope possesses enough sensitivity to detect planetary scale signals within the Alpha Centauri environment. That result directly supports strategies now being refined for observations involving Proxima b. Capability matters. The telescope's greatest advantage comes from infrared sensitivity. Infrared light occupies the exact region where many atmospheric fingerprints appear. Molecules absorb and emit specific wavelengths, leaving subtle signatures within the light passing through or reflecting from an atmosphere. Those signatures can reveal composition. Water vapor, methane, carbon dioxide, and ozone each leave distinctive patterns. If an atmosphere surrounds Proxima b, its strongest clues are expected within wavelength ranges the James Webb Space Telescope was specifically engineered to examine. But extracting those clues remains extraordinarily difficult. Even a relatively dim red dwarf star overwhelms the reflected light of a nearby rocky planet. At a distance of 4.24 light-years, the separation between star and planet appears vanishingly small. Coronagraphic observations push the telescope close to the limits of its operational performance. Yet each observation teaches something new. Every attempt refines techniques, improves data processing, and reveals where future instruments must become stronger, preparing the way for observatories designed from the beginning to study worlds like Proxima b, rather than adapting existing tools to the challenge. A mountain is being reshaped for a question. High in Chile's Atacama Desert, atop Cerro Armazones, at an elevation of 3,046 meters, which is about 1,891 miles, engineers are assembling an instrument unlike anything astronomy has ever possessed. Piece by piece, steel, glass, and precision optics are becoming the extremely large telescope. The scale is difficult to grasp. Its primary mirror will span 39.3 meters, which is about 24.4 miles. That diameter is more than 4 times greater than any optical telescope operating today. Hundreds of mirror segments will function together as a single reflective surface, collecting light that has crossed immense distances before finally reaching Earth. Every photon matters. Compared with the Hubble Space Telescope, the extremely large telescope will gather roughly 100 times more light. Faint signals currently buried beneath noise may suddenly become measurable. Objects that today appear as uncertain hints may become observable targets. The telescope is approaching reality. First light is expected during the later years of the 2020s, followed by full scientific operations during the early 2030s. Unlike many concepts discussed in astronomy, this observatory is not a distant vision awaiting funding. Construction is underway. Foundations exist. Structures rise above the desert floor. And Proxima b is waiting. Among the observatory's most important instruments is the high angular resolution, monolithic optical, and near-infrared integral field spectrograph. The name is lengthy, but its purpose is straightforward. It separates incoming light into its component wavelengths, allowing astronomers to identify the chemical fingerprints hidden within that light. Those fingerprints reveal atmospheres. In 2024, Sophia Vaughn and collaborators published detailed modeling examining what this instrument could detect from Proxima b. Their work focused on reflected starlight, searching for traces of oxygen, water vapor, carbon dioxide, and methane. Each molecule leaves evidence. When light passes through an atmosphere, specific wavelengths are absorbed. The resulting gaps within the spectrum act like signatures. By measuring those signatures precisely, astronomers can infer what gases surround a distant world. The results were encouraging. The simulations suggested that an oxygen-rich atmosphere on Proxima b could be detected if sufficient observing time is devoted to the task. The required observations would span tens of hours across multiple nights, gathering enough photons for statistical confidence. Patience becomes a scientific tool. The same studies indicated that ozone could also reveal itself. Ozone is a molecule composed of 3 oxygen atoms, and it absorbs light at characteristic wavelengths that fall within the instrument's operational range. Detecting such a feature would provide important clues about atmospheric chemistry and long-term stability. But the deeper significance extends beyond chemistry. For the first time, humanity is building an observatory capable of moving the discussion beyond models and probabilities. The extremely large telescope may transform questions about Proxima b into measurements. Atmospheric composition could become data rather than speculation. And once detection becomes confirmation, the conversation changes completely. We are no longer asking whether the nearest potentially habitable world exists. We begin asking what its existence means for science, for civilization, and for our place among the stars. Imagine a spectrum arriving first. Not an image, not a message, not a declaration. Somewhere inside a sequence of measurements, astronomers notice a pattern that should not be there. A handful of wavelengths appear weaker than expected. Certain atmospheric gases seem present in proportions that resist easy explanation. The finding begins as a discrepancy, nothing more. The first response would be restraint. Researchers would compare the signal against models of volcanic chemistry, atmospheric circulation, stellar radiation, and photochemistry, the chemistry driven by light interacting with gases. Every known non-biological pathway would be examined before anyone seriously discussed life. But curiosity would spread. A signal that survives initial scrutiny would be flagged for follow-up observations. Telescopes on different continents would repeat the measurement. Independent teams would analyze the data using separate software pipelines. Observations would be gathered across multiple nights and multiple observing campaigns, searching for consistency rather than excitement. Reproducibility matters. If the feature appeared again and again, confidence would grow. Yet confidence alone would not be enough. Scientists would ask whether an unfamiliar geological process could create the same atmospheric fingerprint. They would investigate whether interactions between radiation and atmospheric molecules might mimic biology without any living organisms being present. Alternative explanations come first. The challenge is that nature often imitates its own mysteries. Methane can emerge from biology. It can also emerge from geology. Oxygen can be associated with living systems. Under unusual circumstances, it can accumulate through non-biological processes as well. Every candidate biosignature exists within a landscape of competing possibilities. But the investigation would deepen. Additional spectral observations would search for supporting gases. Researchers would look for combinations that reinforce one another. A single molecule can be ambiguous. Several molecules existing together in persistent disequilibrium, meaning a chemically unstable balance maintained over time, become far more difficult to explain through ordinary planetary processes. Years could pass. The scientific community carries memories of previous false alarms. Claims regarding life signatures in meteorites generated intense debate. Several exoplanet discoveries required revision after further analysis. The anomalous radio signal, detected from the direction of Proxima Centauri, attracted worldwide attention before a more conventional explanation emerged. Those experiences shaped a culture of caution. Careful language would dominate. Eventually, if every test continued pointing in the same direction, the evidence would move beyond individual research groups. International panels of astrobiologists, planetary scientists, atmospheric chemists, and observational astronomers would examine the complete record. Data would be challenged repeatedly. Assumptions would be questioned. Every weakness would be exposed. Then a statement would emerge. It would likely avoid dramatic words. Scientists would not announce certainty where certainty remains unreachable. Instead, they might conclude that the atmospheric composition of Proxima b is inconsistent with known abiotic chemistry and consistent with biological metabolism. A single sentence. But when those words are finally spoken, after years of verification and scrutiny, every person alive will understand their meaning. Across Earth, people will remember where they were when humanity first learned that life may exist beneath another sun. Step away from Proxima b for a moment, and the picture changes scale entirely. What first appeared to be a single nearby world begins to look like a representative of something vastly larger. The star it orbits belongs to the most numerous stellar population in the Milky Way. Red dwarf stars account for roughly 3/4 of all stars in our galaxy. Out of an estimated 100 billion stars, most belong to this small, long-lived category. They dominate the census. Over the last 2 decades, planet hunting surveys steadily transformed our expectations. Data from the Kepler Space Telescope, combined with later observations from ground and space-based instruments, revealed that rocky planets around red dwarf stars are common. In many cases, they appear remarkably common. Statistical studies suggest that habitable zone planets may exist around a substantial fraction of these stars. The implication is difficult to ignore. A nearby example sits within the system known as TRAPPIST-1, located about 40 light-years from Earth. 7 rocky planets circle that small star. Three of them, designated TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, occupy the region where temperatures could permit liquid water under suitable atmospheric conditions. Their arrangement feels familiar. Those worlds orbit close to their star, just as Proxima b does. Because of that proximity, gravitational forces almost certainly locked their rotations long ago. One hemisphere continually faces the star. The opposite hemisphere continually faces away. The same basic geometry appears again and again. What we have explored around Proxima b, therefore, extends far beyond a single planetary case study. Terminator zones, those narrow regions between permanent daylight and permanent darkness, may be recurring environments throughout the galaxy. They are not rare exceptions created by unusual circumstances. They emerge naturally from the architecture of red dwarf planetary systems. But that realization carries weight. If biology can establish itself in such regions, then habitability expands dramatically. The number of potentially living worlds would no longer be limited primarily to Earth, like planets orbiting stars resembling our Sunday. Entire populations of red dwarf systems would enter the conversation. The numbers become enormous. Hundreds of billions of rocky planets may exist across the Milky Way. Even if only a modest fraction possess suitable atmospheres, stable water cycles, and active geology, the potential inventory of living environments grows to a scale that challenges intuition. This is why Proxima b matters so deeply. Every constraint researchers establish there becomes a tool for interpreting other worlds. The radiation tolerance required of life, the atmospheric conditions needed for surface stability, the spectral fingerprints expected from a biosphere, all become reference points. Future observations from the extremely large telescope and the proposed Habitable Worlds Observatory will rely on that framework. A new scientific discipline is taking shape. Researchers are no longer asking whether red dwarf planets exist. They are asking how to evaluate them systematically as living worlds. Proxima b serves as the calibration target, the nearest laboratory for questions that may apply across the galaxy. Yet after all that expansion, our attention returns to a single destination. Among the countless possibilities scattered through the Milky Way, the first world inviting those questions waits only 4 light-years away. A distance of 4 light-years sounds small on a galactic map, yet across that narrow gulf, an unanswered question has been gathering weight for decades. Physicist Enrico Fermi framed it in the middle of the 20th century with a deceptively simple challenge. If the universe is ancient, if planets are common, and if life has many opportunities to emerge, where is everybody? The question remains. Now it has a location attached to it. Proxima b gives the paradox a specific address. We are no longer wondering only about hypothetical worlds scattered through distant regions of the galaxy. We are looking toward a planet that has existed for roughly 4,850,000,000 years, orbiting the nearest star beyond our own. Time matters here. On Earth, life appeared remarkably early. Complex organisms arrived much later. Technological civilization emerged only in the final fraction of planetary history. Even so, radio technology developed within a period so brief that it occupies almost no space on a geological timeline. A cosmic instant. If life began early on Proxima b and followed a path leading toward technology, then immense spans of time were available. Civilizations could have risen and vanished. Others might have endured. Some could have advanced beyond forms of communication we currently understand. But we have detected nothing confirmed. That absence creates several possibilities, each scientifically credible. The first is also the simplest. Life may exist there only as microorganisms, oceans rocks, and atmosphere could host rich biochemical activity while never producing intelligence or technology. Such a world would still be extraordinary. Another possibility reaches further. Complex ecosystems may have evolved, perhaps with intricate food webs and sophisticated organisms, yet never produced a species interested in engineering, mathematics, or long distance communication. Intelligence is not inevitable. Earth demonstrates only one outcome among countless evolutionary pathways. A different world could favor entirely different strategies for survival and success. But red dwarf environments introduce another possibility. Repeated radiation events may impose a biological barrier. Complex organisms could emerge only to face recurring environmental stress that limits long-term technological development. Some researchers describe such barriers as great filters, obstacles that prevent many worlds from progressing beyond certain stages. The idea remains speculative. There is also the stark possibility that Proxima b is lifeless. Habitable conditions do not guarantee biology. Suitable temperatures, liquid water, and atmospheric stability may create opportunity without ever producing living systems. Nature offers no promises. One final explanation lingers at the edge of the discussion. Life may exist, intelligence may exist, technology may exist. Yet, those civilizations might not broadcast powerful radio signals, or they may communicate through methods we have not learned to recognize. Our instruments search for familiar patterns. The deeper significance of Proxima b is that the silence is no longer abstract. It comes from a known planet circling a known star. 4 light-years away sits a world that may answer one of humanity's oldest questions. For now, it remains wordless, and every possibility still fits within that remarkable silence. Begin with a horizon that never changes. You stand within the narrow belt where day and night meet, a region defined by physics rather than geography. Nothing here requires invention. Everything follows from the planetary conditions researchers have modeled. Around you stretches a landscape illuminated by a star that occupies a permanent place in the sky. It never rises. It never sets. Proxima Centauri hangs low above the horizon, fixed in position throughout an entire lifetime. From this distance, its apparent size is roughly 3 times larger than our moon appears from Earth. Yet, despite that larger disk, it does not flood the world with brilliant daylight. Its light carries a deeper hue, concentrated toward the red and near-infrared portion of the spectrum. Human eyes would miss much of it. The visible sky would likely glow with muted reddish-orange tones. Atmospheric scattering, the process by which molecules redirect incoming light, behaves differently under this stellar illumination. Blue skies, like those familiar on Earth, become less dominant. Longer wavelengths shape the appearance of the air itself. The colors feel unfamiliar. Across the terrain, a steady wind moves continuously. It is born from the permanent temperature contrast between hemispheres. Warm air rises on one side of the planet. Cooler air sinks on the other. The atmosphere circulates between them in patterns that may have persisted for immense spans of geological time. There is no afternoon lull, no seasonal shift, no waiting for changing weather driven by a moving sun. The planetary engine remains active every moment, powered by the same geometry day after day. Turns slowly away from the star. The transition toward darkness arrives quickly. Behind you, the sky deepens through shades of crimson and charcoal before opening into blackness. Stars emerge, even while the red dwarf remains visible near the opposite horizon, Along that darker direction, the Milky Way stretches across the sky with extraordinary clarity. Nothing washes it out. Among those distant points of light sits another star. It appears unremarkable at first glance, yet that star is our Sunday. Seen from Proxima b, it would rank among the brighter stellar objects in the sky, shining as a distant beacon from a different shore of interstellar space. Home reduced to a point. Now consider the experience of any organism evolving here. Every creature on Earth inherited biological rhythms shaped by cycles: sunrise and sunset, summer and winter, day and night. The movement of celestial objects became nature's clock. Those clocks do not exist here. An organism born in the terminator region would never witness its star crossing the sky. It would never learn the meaning of dawn. It would never experience the return of spring. Time would still exist, measured by growth, metabolism, and change, yet many of the astronomical markers that guided Earth life would be absent. And so we remain here for a moment, beneath an unmoving star, within an atmosphere flowing along ancient paths. The light stays constant, the wind continues, the horizon holds its position, 4 light-years away from Earth. A world shaped by different rules reveals just how strange a nearby planet can become. Consider how recently this story began. For thousands of years, human beings watched the night sky and recorded its patterns. Sumerian astronomers traced stars onto clay tablets. Builders aligned stone monuments with celestial motions. Generations mapped the heavens with the unaided eye, then with lenses, cameras, and radio receivers. Through all of that history, Proxima Centauri remained where it had always been, 4.24 light-years away, and we had no idea. A planet circled that star throughout the rise and fall of civilizations. It completed orbit after orbit, while languages emerged, empires expanded, and science slowly learned to measure the universe. Yet Proxima b entered human knowledge only within the past decade. That realization changes scale. The world we have spent this journey examining is neither newly formed nor newly discovered in any cosmic sense. Only our awareness is new. The planet itself has been there all along, accompanying humanity's entire recorded history without announcing its presence. Even now, distance shapes every fact we can know. The light arriving from Proxima Centauri tonight did not leave the star tonight. It began its journey 4.24 years ago. By the time it reaches our telescopes, it already belongs to the past. Every observation carries an unavoidable delay imposed by the structure of space itself. We never see the present. We see messages in transit. Any atmosphere circling that world, any weather moving through its skies, any chemistry unfolding across its surface is hidden behind that interval. Information must cross the gulf before it can become knowledge. Physics permits nothing faster. The same limitation applies in the opposite direction. Humanity has been filling space with radio transmissions since the middle of the 20th century. Television broadcasts, radar systems, scientific communications, and countless other signals have expanded outward as a growing sphere of electromagnetic radiation. But that sphere has limits. Its leading edge is only now approaching the nearest stellar neighborhood. Within the coming decades, some of the earliest detectable transmissions from Earth will finally reach the Proxima Centauri system. For the first time, our closest stellar neighbor will receive evidence that a technological civilization exists here. Whether anything is there to notice remains unknown. Whether such a signal could be recognized remains unknown. Whether recognition would matter remains unknown. And if a response were somehow generated immediately, it would still require another 4.24 4 years to return across the darkness between stars. Conversation, in the ordinary sense, becomes impossible. Patience becomes mandatory. The distance demands it. So we arrive at a remarkable situation. A potentially habitable world circles the nearest star beyond our Sunday. We know its mass, we estimate its environment, we model its atmosphere and imagine its possibilities. Yet the most important questions remain untouched. No answer has crossed the gap. For now, 4 light years is not merely a measurement. It is a boundary between knowledge and uncertainty, carrying the weight of every possibility that still waits beyond our reach. Sometimes, a discovery changes science before it answers a single question. Proxima b occupies that rare category. Long before any confirmed biosignature, long before direct images, and long before a spacecraft reaches its destination, this nearby world has already altered the direction of research across multiple fields. The influence is measurable. It appears in budgets, telescope designs, published papers, and engineering proposals. The planet changed priorities. When astronomers announced its discovery in 2016, the nearest potentially habitable world suddenly acquired a name, an orbit, and a location. The search for life was no longer focused only on distant statistical populations. It gained a specific destination. Researchers could build models around an actual planet rather than a hypothetical one. That shift mattered. One of the clearest examples emerged almost immediately. Breakthrough Starshot, unveiled in 2016 by Stephen Hawking, Yuri Milner, and Mark Zuckerberg, proposed the first peer-reviewed framework for reaching another star system within a human lifetime. Interstellar travel had often occupied the realm of distant speculation. Proxima b transformed it into a defined engineering challenge aimed at a known target. The planet influenced institutions as well. Questions surrounding red dwarf habitability moved closer to the center of planetary science. Researchers within the National Aeronautics and Space Administration and the European Space Agency increasingly focused on atmospheric survival, magnetic shielding, stellar activity, and the biological consequences of long-term exposure to red dwarf radiation environments. New investigations followed. Scientific teams across North America, Europe, Asia, and Australia began examining how life might function under conditions rarely considered in earlier habitability studies. Papers explored radiation-resistant microorganisms, atmospheric circulation on tidally locked planets, magnetic field evolution, geological stability, and photosynthetic systems adapted to near-infrared light. Each study expanded the map. The influence reached telescope development as well. Instruments intended to analyze nearby exoplanets increasingly considered Proxima b as a benchmark target. Spectral resolution requirements, observing strategies, and atmospheric detection thresholds were evaluated against the challenge of identifying possible biosignatures around the nearest known rocky world beyond our solar system. Even computational research reflects this shift. A landmark biosignature simulation produced by the National Aeronautics and Space Administration in 2024 applied advanced climate modeling and detectability analysis to a specific named exoplanet. Proxima b served as the focus because its proximity offers the strongest opportunity for future verification. But perhaps the most significant change is harder to quantify. For generations, discussions about extraterrestrial life often unfolded at immense distances, scattered among countless stars across the galaxy. Proxima b narrowed the scale. The question moved closer. It became attached to a place orbiting the nearest stellar neighbor, a star visible from southern skies and reachable by instruments already under construction. The search acquired an address. And through all of this, one remarkable fact remains unchanged. Proxima b has not yet revealed whether it hosts life, oceans, a stable atmosphere, or anything biologically active at all. Yet, even in uncertainty, it has reshaped science. Sometimes a question changes the world before the answer arrives. Strip away the planets, the stars, and the distances for a moment, and we arrive at a simpler question. What is life? Astrobiology offers a working answer rather than a final one. Life is generally defined as a system capable of metabolism, meaning it extracts and uses energy. Self-replication, meaning it produces copies of itself. And Darwinian evolution, meaning those copies vary and can be shaped by natural selection across generations. Everything alive on Earth fits that description. Bacteria fit it, trees fit it, whales fit it, human beings fit it. Across billions of years of evolutionary history and an astonishing diversity of forms, those three properties remain universal. But there is an important limitation. That definition emerged from a sample size of one. Every example we have ever studied belongs to a single biosphere on a single planet. We often speak about life in general terms, yet our understanding is built entirely from Earth. We do not know whether our definition captures a universal principle or merely describes the particular path biology followed here. That uncertainty follows us to Proxima b. The planet exists under conditions that differ from those of Earth in important ways. The dominant wavelengths reaching its surface are different. The radiation environment is different. Gravity is different. Atmospheric circulation may be different. Water, if present, likely moves through unfamiliar patterns shaped by a permanently fixed stellar geometry. Evolution would respond. Yet beneath those differences lies a deeper layer that does not change. Carbon retains the same chemical properties everywhere in the universe. Water behaves according to the same physical laws. The thermodynamics of energy extraction, the rules governing chemical bonds, and the mathematics of information storage remain constant from star to star. Physics travels well. Chemistry does too. If life emerged on Proxima b, it would almost certainly confront the same fundamental challenges faced by every living system. It would need to gather energy from its environment. It would need to preserve information. It would need to reproduce with sufficient accuracy to persist and sufficient variation to evolve. The solutions might look unfamiliar. Pigments could differ dramatically from those found on Earth. Molecular repair systems might operate with efficiencies beyond anything known in terrestrial organisms. Sensory structures could be adapted to wavelengths our eyes cannot perceive. Methods of movement, communication, and environmental awareness might follow pathways evolution never explored here. But those differences belong to expression. The underlying logic remains. Natural selection would still reward successful strategies. Information would still compete against entropy. Energy would still flow through living systems. The details could vary endlessly, while the foundation stays recognizable. And that leads to a remarkable possibility. If something lives beneath the light of Proxima Centauri, it may appear alien in countless ways, yet at the deepest level, it would not be our opposite. It would be another outcome of the same physical laws that shaped every organism on Earth. Across 4.24 light-years, separated by a different star and a different history, two branches of biology would still belong to the same universe, sharing the same chemistry, the same constraints, and perhaps the same fundamental story. A planet circles the nearest star beyond our Sunday. That statement alone would have sounded extraordinary for most of human history. Today, it is simply a fact. We know the planet exists. We know its mass, we know its orbit, we know it receives enough stellar energy that liquid water remains physically plausible under the right atmospheric conditions. We know chemistry can operate there. We know billions of years have passed there. And that is why scientists consider life possible. The answer to the question posed at the beginning of this journey is surprisingly direct. Researchers think unusual life could be hiding on Proxima b because the conditions are not impossible, the chemistry is not forbidden, and the timescale available for biological evolution is immense. Every model developed so far leaves open a path, narrow in some cases, broader in others, through which living systems might emerge and persist. Those systems would likely differ from us. Different wavelengths dominate the environment. Different evolutionary pressures shape adaptation. Different atmospheric conditions influence metabolism and survival. The underlying chemistry may remain familiar while the expression becomes something entirely its own. But beneath that answer rests a deeper question. It is the question that has lingered behind astronomy, biology, and philosophy for generations. Is life a rare accident, dependent upon an improbable chain of events? Or is life a natural consequence of chemistry whenever energy flows through matter long enough? Proxima b matters because it transforms that question. For the first time, the discussion is anchored to a specific destination. We are no longer pointing toward a hypothetical world around an imagined star. We are examining a confirmed rocky planet orbiting the confirmed nearest star beyond our own. The question has an address now, a real one. If future observations reveal convincing evidence of biology on Proxima b, the implications would extend far beyond a single planet. Independent life emerging twice within the same local stellar neighborhood would suggest that biology may arise readily when conditions permit. The numbers become difficult to grasp. Across a galaxy containing hundreds of billions of stars, living worlds could be extraordinarily common. But another possibility remains. Proxima b may prove barren. Its atmosphere could be absent. Its surface could be hostile. Its history could have unfolded in ways unfavorable to biology. Yet even that outcome would leave the larger question unresolved. One world cannot represent an entire galaxy. A single negative result tells us little about countless other environments spread across the Milky Way. Science accepts that uncertainty. It works within it. That is why telescopes continue observing, why instruments continue improving, and why researchers continue refining models year after year. Each new measurement reduces the space occupied by ignorance. Each observation narrows possibilities. Each dataset turns speculation into evidence. So where does that leave us tonight? The most honest answer remains unchanged. We do not know. But for the first time in the history of this question, the gap between those words and an answer has become measurable. The distance is no longer philosophical. It is technological. It is observational. It is a challenge of instruments, patience, and time. And across 4.24 light years, a real world waits within reach of our growing understanding. A child born today may one day read a scientific paper that answers a question older than civilization itself. That possibility is new. For thousands of years, people looked upward and wondered whether life existed beyond Earth. The question survived changing languages, empires, religions, and technologies. It passed through the astronomers of ancient Mesopotamia, through the builders of Stonehenge, through the inventors of telescopes, and through every generation that mapped the sky with increasing precision. Yet none of them possessed a realistic path toward an answer. They could ask, they could imagine, they could debate, But the necessary instruments did not exist. We live in a different moment. For the first time, the question has moved from philosophy into measurement. The uncertainty remains, yet the tools required to confront it are already being assembled across deserts, observatories, laboratories, and engineering facilities around the world. Some are rising now. The extremely large telescope is expected to begin producing scientific observations during the coming decade. Its enormous mirror and advanced instruments are being designed to extract atmospheric information from nearby worlds, including Proxima b. If oxygen, methane, water vapor, carbon dioxide, or ozone leave detectable fingerprints there, researchers will search for them directly in the reflected light of the planet. But that is only one step. The proposed Habitable Worlds Observatory represents another leap forward. If funded and completed on its current trajectory, it could directly image nearby rocky planets and examine them for biosignatures with a sensitivity unavailable today. Instead of inferring the existence of a world through indirect methods, we may study light coming from the planet itself. The pace is accelerating. Meanwhile, concepts once confined to speculative engineering studies are becoming increasingly detailed. Interstellar probe designs continue to mature. Researchers examine propulsion systems, communications methods, materials science, and miniaturized instruments capable of surviving journeys beyond the solar system. A mission inspired by the breakthrough Starshot concept could potentially reach the Proxima Centauri system during the second half of this century and return close-range observations before the century ends. Think about who will receive those transmissions. Many are already here. Some are graduate students beginning their careers. Others are children learning basic astronomy in school. Some have not yet decided what they will study, what they will build, or what questions they will pursue. Yet the people who may analyze the decisive spectra, publish the landmark papers, and announce the strongest evidence are walking the earth right now. You may be one of them. The answer will probably not arrive tomorrow. It may not arrive next year. Scientific progress rarely unfolds according to human impatience. Verification takes time. Observation takes time. Understanding takes time. But the horizon has changed. The universe has held this particular secret for roughly 4,850,000,000 years. Across nearly all of that span, no species existed that could even formulate the question. Now, one does. Now we are building the instruments. Now we are looking directly toward the nearest possible place where an answer might wait. On the scale of cosmic history, the remaining wait is remarkably short. Some mysteries are hidden at the edge of the universe. Others wait much closer. Only 4 light years separate us from Proxima b, a distance that sounds small when spoken aloud, a distance so vast that every message crossing it spends years in transit. Between those two truths hangs a question humanity has carried for as long as it has looked upward. Are we alone? The star itself is unremarkable at first glance. From the southern half of Earth, under dark skies and with patient observation, Proxima Centauri appears as a faint reddish point among countless others. For all of recorded history, it occupied its place in the heavens without drawing special attention. Kingdoms rose beneath it. Languages emerged and vanished beneath it. Entire civilizations lived and disappeared beneath its light. The star remained. Night after night, century after century, generations studied the sky, mapped constellations, predicted eclipses, and measured planetary motions. They wondered whether other worlds existed around distant suns. They imagined possibilities. They told stories. Yet all the while, a rocky planet circled our nearest stellar neighbor, unknown to every observer who ever lived. We learned of its existence only recently. Less than a decade has passed since its discovery. In that brief span, the pace of progress has been extraordinary. Scientists moved from detecting the planet to modeling its atmosphere. Researchers simulated possible biospheres. Engineers refined telescope designs intended to search for signs of life. Teams developed serious proposals for interstellar probes aimed at the system itself. The question accelerated. Human curiosity found a target. But the most remarkable part may be how ordinary the process feels. Observatories gather data, computers process spectra, researchers debate interpretations, engineers improve instruments. The search advances through patient work rather than dramatic revelation. One measurement at a time, one observation at a time. Meanwhile, Proxima b continues its orbit. Whatever exists there, whether oceans or bare rock, whether chemistry alone or something more, continues according to its own history. The planet does not know it has become the focus of scientific attention across another world. Yet our attention remains fixed, because the answer matters. If life exists there, then biology emerged independently within our own cosmic neighborhood. The universe would appear far richer than many once imagined. If the planet proves barren, that result also teaches us something profound about the conditions required for living systems to arise. Either outcome changes us. The mystery remains unresolved tonight, but it no longer belongs to a distant age of speculation. It belongs to the working future of scientists already operating telescopes, building instruments, analyzing data, and preparing the next generation of observations. And so we return, one last time, to that nearby star and its unseen companion. 4 light-years away, beneath a sky that never changes in quite the way ours does, a world circles through unbroken ages. We look toward it from across the darkness. It remains there, carrying its answer. And that answer is coming. Above us, the same sky stretches on. Somewhere within it, beyond the reach of the eye, but not beyond the reach of understanding, the nearest mystery waits.